Okay, this time we're going to be taking a look at the stiffness metrics for 2D frame. So we've already completed 2D dress. Now we're going to be taking a look at 2D frame. Okay, so at first let us consider a member. So this is the member. This member is AB, which is subjected to a few forces that are seen here: XA, YA, MA, XB, YB, MB, where MA and MB are two moments. Okay, so the joints of member AB, the A joint and B joint, are both subjected to this forces. Okay, so since there are three types of deflections, since there are three types of forces, there are two forces in one moment, so there are going to be three types of deflections, two displacements, and one rotation. The rotation is actually coming because of the moment. Okay, so if we assume that the length of the member is L and its modulus of elasticity is E and cross-sectional area is A and moment of inertia about Z axis is I, then we're going to get the following matrices. So the stiffness matrix, the axial stiffness matrix Sx is equals to Ea by L. Then we have the shear stiffness matrix S1, which is 12 EI by L cube. Then we have S2, which is also a shear stiffness matrix, that is 6 EI by L squared. Right after that we have S3, which is a flexural stiffness. So we have the flexural stiffness 4 EI by L, and S4, which is also flexural stiffness, which is 2 EI by L. So this S1, S2, S3, and S4 stiffnesses are the reasons for the stiffnesses are similar for the reasons that you have seen in the moment distribution method or the Hardy-Cross method. Okay, so these are not really a topic of here, and since we're going to be developing the formula, if you don't know the Hardy-Cross method, or if you have not encountered the S1, S2, S3, S4 before previously, if you have not done the Hardy-Cross method or the moment distribution method, then you don't need to really worry about them, because they're just required to show you the actual metrics, and once we have developed the metrics, we don't need to really know how these things are developed. You can just use the metrics as a formula to solve the problems. Okay, so let me just erase this and let's move on. Okay, so we have seen that there are 6 unknown forces: XA, YA, MA, XB, YB, MB. Now if we move on, we can see that the unknown forces that are here are actually at the joint. Those are actually being applied at the joint. Now if the member had some forces, for example, not on the joint, on the body of the member, so this is member A, B. So let's say the member had some sort of load, UDL, a distributed load, on its body, or perhaps it had a point load on its body, right? So how are you going to tackle that load? We're going to have to mention that load as well. So this is actually also coming from the moment distribution method or the Hardy-Cross method, where we have seen that. Let me just erase this and we'll continue. Okay. Similar to the Hardy-Cross method, we have seen that if a member had some forces on its body, what we do is we convert those forces into fixed end support reactions. Meaning, if the member does not have any fixed ends, we're going to consider that there are fixed ends, and we're going to convert the load into fixed end support reactions. So if there was a uniformly distributed load W and the length of the member was to be L, then the reactions here would be WL by 2 on this, and here also we're going to have another WL by 2, whilst the moment reactions here and here would have been minus WL squared by 12, and here it would have been WL squared by 12. And if there were a point load on the member AB, you consider the fixed ends. You put a point load here. Let's say the point load was of P, the length is of L, so the reaction forces here have been P by 2, and then the moment reactions here would have been PL by 8, and on this direction it would have been minus PL by 8. Okay, so here when it says that if the displacement and rotation of joints in BR and the fixed end reactions are denoted by FE. So the fixed end reactions, this fixed end reactions, if there was a UDL, the fixed end reaction would have been WL by 2 and this WL squared by 12. These are actually being denoted by FE here, fixed end reactions for X, fixed end reaction for the Y direction, fixed end reaction for the M direction. Okay, alright, so if we consider all of these fixed end reactions are coming because of the loads on the body of the member, and previously we had seen that there were forces on the joints. So 3 forces on A joint, 3 forces on B joint, and if we move up we can see that there are 3 fixed end reactions on A joint, 3 fixed end reactions on B joints. So in total we have 12 reactions. Okay. Alright, so in total we're having 12 reactions. Okay, now if we take a look at these individually, for example, the same way we had done it to address. So this is the UA, the displacement at the A joint, then we have the displacement at the B joint right over here, then we have the displacement at the A joint, the vertical displacement at the A joint VA, we have the vertical displacement at the B joint VB, we have the rotational displacement, the rotational deflection at A joint as theta A, then we have the rotational deflection at B joint as theta B. So these are the diagrams that are showing the displacements. Now if we were to use these diagrams to write up equations that we can turn into matrix form, let's do it for joint A. So f of x at joint A, let's take a look at that. Okay, this is what we're going to take a look at. So for x direction forces at A joint, we have here FEXA. This is a force that is being on this direction. So this is a positive, this is going to be positive according to our sign convention that we have seen at the beginning of the course. So this is positive FEXA. Right after that, at A joint we have another force. So we know that K into U, meaning stiffness into deflection, is equals to force. So Sx is K, meaning deflection, Sx is stiffness, UA is deflection. So if we multiply them, we're going to get force. So here we have Sx and UA, and the direction was in the positive direction, that is why there is a plus there. Okay, right after that we have a 0, because here you can see that there is no forces on the x direction. Similarly, another 0 is going to be for this figure because there are no forces in the x direction, so there are 2 zeros right up there. And right after that we have minus Sx UV, because the Sx at A joint in this part is facing on the negative direction, and the displacement here is UV. So Sx UV, it is negative because it is on the negative direction. Right after that, this figure does not have any x component, neither does this one have any x component. That is why there are 2 zeros there. Okay, so we have developed one equation. So let me just erase all this and let's continue on to see the next equations. Okay, this time let's develop the y direction forces equation for joint A. Okay, at joint A we have FEYA positive, so FEYA positive. Then here there are no vertical forces, so there's going to be a 0, there goes 0. And here at A joint we have S1, and multiply that by VA, we're going to get the force. So S into V is equal F, right? So that is why we're going to multiply SA into VA. So there we go, SA into VA, since it is an upward force, it is positive. Right after that we have S2 theta A. S2 theta A is coming from this figure. At A joint we have the vertical force S2, which is now going to be multiplied with this theta displacement. So theta is a rotation, but it still is deflection, right? That is why it is being multiplied here. So we have S2 theta A, and then this figure does not have any vertical forces, so there is going to be 0. And here at A joint there is a force, but it is on the downward direction. That is why there is going to be a minus, and the and that is S1 into VV. That is the force S1 into VV. So we have S1 VV. Right over that, in this figure at point A, we have a positive force S2 into theta B. So we have S2 into theta B. So that was the equation for FYA. Okay, now let's take a look at another equation. Okay, now we're going to be looking at this equation, the rotational equation. So at A joint we have FEMA, so we have FEMA. There you go. Then here we don't have any rotations, so that's going to be 0. But here at A joint, in this figure at A joint, we have a rotation which is the S2 into VA, and since it is anti-clockwise, we had considered anti-clockwise to be positive, so this is going to be a positive moment. So S2 VA, positive moment. Right over that, here we have another moment. This is also anti-clockwise, so this is a positive moment S3, which is going to be multiplied by theta A. So we have S3 theta A. Right after that, in this figure there are no rotations, so the rotation is 0. In this figure we have a rotation which is clockwise, meaning it is going to be minus. We have a minus here, and the rotation is S2 into VB. So we have S2 into VB. Right after that, here at the A joint we have an anti-clockwise. Here we go, anti-clockwise rotation, which is, since it is anti-clockwise, it is going to be positive, and it is S4 into theta B. So we have S4 into theta B. Okay, so we have seen how we are developing these equations. Since I have shown you for the joint A, joint B equations are also similar. The joint B equations are also similar. If you have understand the joint A equations, you can develop the joint B equations yourself. Okay, so do try to develop the equations. And right after we have developed our equations, if we move further on, we can see that we can place the equations into a matrix format, just like we did with the truss. So I'm not wasting any time explaining this here, because we have already explained how we go from equation to matrix. So right over here we have the stiffness matrix. This is the stiffness matrix. This is the displacement vector, and this time we have 2 force vectors instead of 1, because one force is because of the joint forces, and another force vector is because of the fixed end conversions, right? The fixed end moment, sorry, I would call that fixed end reactions. Okay, because of the fixed end reactions. So if I call this K, stiffness matrix K, displacement vector U, and this force, this load vector, we can denote it with Q, and then we can use the fixed end reaction vectors by denoting them with F. Now we already know that KU is equals to F, but in this case we have KU equals to, we're gonna get F if we do Q minus small f, then we're gonna get big F from there. Okay, so this is what we're gonna get. So if we do this, we're gonna get F. Okay, so this is what we are doing. This is what it says right over here. It says KML, the stiffness matrix of member A, local axis system, UML, the displacement vector of the member and the local axis system, and PML, the force vector of the member in the local axis system, and this PML is coming from intersecting FML from QML, right? Equals load vector minus fixed end reaction vector. Okay, so this was the formation of the local matrix for 2D frames. Okay, alright, so that is it for this video. Thank you very much for watching, and I hope you got to learn something new.